Thank you very much indeed for the invitation to speak. I want to talk about my work using mathematical modeling to support outbreak response and pandemic preparedness. I thought it'd be helpful to start by a bit of vocabulary, so explaining what I mean by an outbreak, an epidemic, or a pandemic. And broadly, I mean the occurrence of cases of a disease. And here I'm focusing on infectious or communicable diseases in excess of what you would normally expect. And really the difference between outbreak, epidemic, and pandemic comes in what is the scope of this excess of cases, where outbreak is really something that would be very limited in scope, maybe within an institution, a hospital, for example, or a village or a town. Epidemic would be something that spreads at a region or country level, and pandemic would be at global scale. And sorry, the word continent here has gone a bit wrong and should be with multiple countries. So really they're the same, but at different spatial scales. And if you look at outbreaks of infectious diseases, they're basically everywhere all the time. And so, I don't want you to look at the details of this, but just kind of really think about the sheer scope of these threats that are affecting human health globally on a continuous basis. This means that we have to develop systems for detection of those threats. And I've put this in a little lighter color because my work doesn't focus on detection. There's excellent science around detection of outbreaks. But once you've detected an outbreak, you need to know how to monitor it and how to respond to it. And this is really where my work focuses. So you can see here a plot of schematic cases over time, potentially with multiple waves during an epidemic. And after detection, there are kind of typical questions that we ask, irrespective of what the pathogen causing the epidemic is. The first one is, how dangerous is the pathogen? So some pathogens circulate in a population, but they don't cause clinical disease in people. So we don't really care about those. How quickly is it spreading? This is important because, for the same level of severity, if something spreads very quickly, then you expect more people to be affected. And so the burden is going to be larger. So evaluating that is very important too. Thinking about how you're going to monitor the epidemic's impact. So how are you going to make sure that you see cases, that you see potential deaths, and that you measure different ways in which the pathogen affects the population is very important. And finally, of course, if this is indeed a dangerous and pathogen that is spreading substantially in the population, you want to think about how do you respond to control the epidemic. So this is really where my work focuses. And I want to try and explain why we need what I call modeling, and I'll show an example of that in a minute, to support the answer to those questions. So think about this question. What is the transmissibility or severity of a pathogen that potentially has newly emerged in a population? I would argue that the most natural study designs to address this question are impractical. So in the second part of this seminar, you'll hear about challenge studies, for example, where we deliberately infect individuals with a pathogen to observe what happens to them, basically. And this is very schematic, but you can see already that these studies come with very high ethical challenges. Typically, they will be very small in size, and they will be focused on healthy volunteers. And therefore, that's a very biased population. It doesn't tell us very much about how vulnerable populations would react to this pathogen, how severe that might be in those populations we really care about very much. So although these studies have bring a lot of insights into a pathogen, they don't tell us everything. Similarly, we have other study designs, for example, case control studies, where we compare groups of individuals who have the disease to groups of individuals who don't have the disease. But these typically don't measure how these people then go on to infect other ones. And if we wanted to observe how they go on to infect others, this would come with ethical issues as well, because you would want to stop that spread, right? So there is kind of a balance to be found there. A second question is about what is the population level impact of an intervention package? And again, the kind of natural and gold standard study design there is a clinical trial. And these are invaluable. We need those clinical trials, but often they only measure intervention efficacy at the individual level, not at the population level. And this is very important because if you have, for example, a vaccine trial, it will typically measure how much me being vaccinated protects me against infection or against disease. But if I'm vaccinated, then that might also protect the people around me, because if I don't catch the disease, I won't spread it. And this sort of population or indirect effect is typically not captured by clinical trials. And similarly, clinical trials typically look at one intervention at a time rather than multiple interventions that one might want to carry out at the same time in response to an epidemic. So this is why mathematical modeling is really a very useful tool that complements those other study design to help address those questions. So I wanted to take you through one schematic example, which is what proportion of the population should be vaccinated. And I'm going to assume that we have a perfectly effective vaccine. And I want to know how many people should be vaccinated to control the epidemic. To do that, before I go into how we do that, I'm going to try and explain why this is an important question. So of course, you could vaccinate everybody in your population and then everybody would be protected. But you could also vaccinate everybody except one person. And because everyone else is vaccinated, this one person would be protected by what we call the herd immunity effect. And then you can think about, well, if I can, get away with not vaccinated this one person, can I maybe only vaccinate a proportion? And if so, what is this proportion? So in order to address that question, I need to introduce a parameter that we modelers often use, which is called the basic reproduction number, or R0. This is defined as the average number of secondary cases infected by each case. So if R0 is 1, like in my example, I will infect one person, this one person will infect one person, you have those sort of flat, if you want, epidemic chains. But if R0 is 2, I will infect 2 people, and each of those will in turn infect 2 people, so you can see that the number of cases will rapidly grow. And of course, it will grow faster if you have higher reproduction numbers. And so the rule is that the epidemic grows only if the basic reproduction number is at least 1. So the aim of intervention is to bring that number at 1 or below so that the epidemic stops growing. So coming back to my question about vaccination, if the aim is to just avoid growth, if the basic reproduction number is 1, well, I don't need to do anything because cases are not growing, they're flat. But if I have a basic reproduction number of 2, I hope that you can see through that schematic that if I vaccinate every other case, or 50% or half of the population, this will be enough to flatten the epidemic. Because for each person, instead of infecting 2 people, one of those 2 on average will be protected by a vaccination. And therefore, this person in blue here will be protected. And the gray individuals, which are the cases they would have produced if they hadn't been infected, are also avoided, right? So at each generation of case, I remove one of the 2 secondary infections because I vaccinated half of the population. And this leads to a flat epidemic that no longer grows. You can do the same with an R0 of 3. You need to vaccinate more people, so avoid 2 out of every 3 secondary infections, and therefore you need to vaccinate at least 2/3 of the cases. And we can kind of summarize this through a mathematical formula for what we call the herd immunity threshold, which says that if a disease spreads with a given R0, in order to effectively control the disease, you need to vaccinate at least R0 minus 1 over R0 individuals with a perfect vaccine. So what I've done here is use a sort of mathematical model to derive something that might be very effective to answer a policy question. So if a policymaker comes to me and asks, well, this pathogen is spreading, I have a vaccine, how many people should I vaccinate? Then I am able, through this mathematical thinking, to address this question. And there are many policy relevant questions we can address with modeling. For example, when will the epidemic take off in our country? How many people will be ill or hospitalized or will die? How many hospital beds will be needed in the next month? Should we close schools? Who should be prioritized for vaccination? What interventions will be most effective? And with all of these questions, what I can do is do some analysis. So I'll write a model, which is basically a set of rules about the pathogen, the population in which it's spreading, so trying to account for the behavior of that population, how they interact with one another, and then the potential interventions that we have to control this. We write mathematical rules about how those three elements kind of link with one another, and then we can run the model to produce certain outputs. For example, the model can then predict how many people will be in hospital over time. And very importantly, this is not just a theoretical model, because I can now check that this output of the model, how does it compare with data? Because, for example, hospitalizations over time is something that we might be recording and I might be observing. So I can refine my model and calibrate my model so that it matches what is observed in the real world. That gives me confidence that my model is a good set of rules that reproduces important aspects of pathogen transmission. And I can run the model forward in time, for example, to predict what's going to happen later on. I can run it with different interventions to predict what would be the most effective. And this is how we answer the questions I've outlined. I wanted to give you two examples of some of the work I've done in doing this in the past. One was in response to the Ebola epidemic in West Africa in 2013, 2016. So Ebola is a very severe viral infection that has been known for years and had been spreading mostly on a recurrent basis, but mostly in Central Africa. And in 2013, it emerged in West Africa. And by the time it was detected, the epidemic was already orders of magnitude bigger than any epidemic that had been seen before. So the policy questions there were, how fast is this spreading? Why is the outbreak so large, so much larger than the previous ones? How severe is it? And are current interventions sufficient? So we did some modeling, and we were able to estimate the basic reproduction number for this outbreak, which was around 2. We also estimated that about 70% of the cases were dying, so that was enormous severity. But actually, those numbers were quite similar to previous outbreaks. But because the outbreak had been detected very late, we were projecting very large epidemic sizes if nothing was done. So this is kind of pictured in that with that red dashed line going up very quickly to about thousands of cases projected to happen every week. So what we, in response to the policy questions, found was that the extent of the outbreak and its magnitude was likely due to the fact that it was delayed in being recognized, because those countries had never seen Ebola before, and also the international community responded very late. We found very high severity, but luckily the kind of usual intervention package, which consists in putting people in hospital very early so they're not infectious in the community, was effective, but not 100%. And so it took a long time to kind of contain that epidemic. Perhaps closer to some of the audience's knowledge and experience is the SARS-CoV-2 or COVID epidemic in England, where, again, from early 2020, we were asked how likely is the epidemic to get here when it was initially discovered in China. How transmissible is it? How severe is it? And what could we do about it, really? So we started working on this in early January. And by mid-January, we estimated that the number of cases of the new coronavirus in Wuhan was actually 10 to 100 times larger than was reported at the time. So this was demonstrating, very large pool of potentially infected individuals. And by the end of the month, we had estimated that human-to-human transmission was indeed happening with an R0 around 2.6, so quite high, and therefore we were expecting a rapid growth in cases. In early February, we provided the first estimates of the proportion of infected individuals who die at 1%. So this is much less high than for Ebola, but combined with a high reproduction number, it was clear that this was going to become a very large issue. So we started looking at the potential for interventions, and in mid-March, we produced some projections, modeling projections that projected a very limited impact of any single intervention, demonstrating that probably we were going to have multiple interventions combined in order to be able to mitigate the epidemic. Of course, this then lasted for quite a while. And so after the initial questions for the whole of 2020, 2021, I would say, we had constant questions from policymakers, including in the summer 2020, after the first wave in the UK, questions around whether immunity in the population was enough to prevent another wave. In autumn 2020, when the vaccine trials were coming out with very encouraging results, the question was, is vaccination going to be enough to lift all restrictions? And then in sort of winter 2020 and all the way to the end of 2021, we had recurring questions about variants of concerns. So whether Alpha, Delta, and Omicron, which emerged in succession in the UK, were going to be a problem and what we should do about it. So I'll very quickly synthesize some of the work we did to address those questions. The first one is in the summer of 2020, we estimated the maximum level of immunity acquired by the UK population. This is shown in this map, and you can see that it was at most 20%. And this really wasn't sufficient, according to our modeling, to prevent another wave alone. So that led to sort of a tier system, and then with the emergence of Alpha, actually led to a lockdown at Christmas 2020, if you remember. But at the time, remember, vaccination was starting to be an option. And so we did some work that showed that actually, despite the high efficacy of the vaccine, vaccination was not going to be a magic bullet. And the reason was that it was going to take quite a long time to vaccinate the whole population. And therefore, we suggested that restrictions needed to be lifted gradually. And the government then decided to design this roadmap out of lockdown, which was a stepwise plan for lifting the restrictions. But in spring 2020, the Delta variant emerged, and we found, again, through modeling, that it was transmitting more and that it was likely to cause another large wave of hospitalizations, but that delaying this step 4 of the roadmap would help to mitigate that new wave. And so indeed, the government again decided to delay this step 4 of the roadmap. So what I want to say now is that we can't predict what the next epidemic will be, but we can do many things to be better prepared, drawing from what we've learned with those outbreak responses and using modeling for outbreak response. The first thing is that we can predict what policy questions will emerge in future outbreaks, irrespective of what pathogen emerges and where. And this will broadly be around what's the likely public health impact of the outbreak, and that'll be driven by how severe and transmissible the pathogen is, and then how feasible is control, and that'll be driven by the interventions we have in place. And with modeling, we can model what the population impact of those would be. We can also create statistical methods and software tools that enable automatic analysis to answer these questions. And in my department, we create a lot of those packages. You can see some little kind of images here. And I wanted to mention one which I created called EpiEstim, which was used in Ebola, used in COVID. And it's really a very useful and really easy to use tool for tracking pathogen transmissibility in real time. The good thing about it is it's easy to use and not pathogen specific. We can also ensure that the required data is collected to answer the questions of policymakers. And this is a table I drew after Ebola in West Africa to try and highlight exactly what data allows to answer what question. And I think this is one step, but there is a lot more work that can be done using modeling to design effective surveillance systems for the future. And finally, in recent work, what we've tried to do as well is synthesize the knowledge on high-threat pathogens that already exist. The WHO, for example, has a list of high-threat pathogens. And what we've done is created a software package, which is basically a live library of mathematical models and epidemiological parameter estimates for pathogens that already exist and that we know, because they're very deadly or very transmissible, they might become a threat to the population. So in green are the ones that we've already reviewed. The knowledge for yellow is in progress, and red is still to come. So in conclusion, mathematical modeling is a useful complement to traditional epidemiological studies. It helps characterize the threat posed by a new or re-emerging pathogen and to evaluate and compare interventions. It's often used in real time to address policy questions during an outbreak. And something I really wanted to mention is it's even better when you have different modeling groups working on trying to answer the same policy question, because if their results are consistent, then it reinforces the strength of evidence for policymakers to then consider. And of course, all of that experience acquired through responding to outbreaks can then in turn support pandemic preparedness. And mathematical modeling is a huge part of that. And I'd really like to emphasize the important role I think mathematical modeling should and can play in shaping surveillance systems. And I think there's still a lot to do there. So I'm very excited to continue work in that area. I'll thank my colleagues on all the work I've presented, thank funders, and finish there. Thank you very much.